Next we are going to look at invariance of stress. When we looked at the Mohr circle equations in the previous lectures, what we found was this quantity trace of sigma does not change with the coordinate direction, right. Similarly, we found that trace of sigma square does not change with the coordinate directions. Okay, I gave an exercise for you to see that trace of sigma square does not change with the coordinate direction changes. Okay, the value of this trace of sigma square, and determinant of sigma is also one such quantity which does not change with the coordinate direction changes. Okay. So, these are called as invariance of stress. These quantities that does not change with the coordinate direction invariance of stresses are function of stress whose value is not dependent on the coordinate system used to represent the stress tensor. Okay. Any function, any trace of sigma power n will be a invariant, okay. But there are what is called as principal invariants of stress which is denoted by K1, this is trace of sigma, K2 which is 1 of trace sigma whole square minus trace of sigma square, and K3 which is determinant of sigma. Okay. This K1, K2, K3 are called as the principal invariants of the stress tensor. Okay. That is, these values does not depend on the coordinate system. The value of K1, K2, K3 is independent of the coordinate system used to represent the stress tensor. Okay. Now, let us look at how does this principal invariance of stress arise. Okay. For that, we have to understand, go back and look at what normal stress is, and we want to find the extremum normal stress that will lead to a characteristic equation which will contain these invariants. Okay. So, let us do that. Now, what is normal stress acting on a plane? This will be sigma transpose n dotted with n, that is nothing but the traction dotted with n. Okay. I want to find n. Question is find n such that sigma of n is maximum. Okay. You know that n should be a unit vector, so you want the norm of n to be 1. Okay. So, what does this mean? Sigma, the tensor sigma is given, you have to find the 3 components of n1, n2, n3 of n such that this quantity sigma n dotted with n is maximized. Okay. Since you have a constraint that the magnitude of n has to be 1, you are the what you do is you do a constraint optimization, that is you define an auxiliary function L such that it is sigma transpose n dotted with n minus lambda to n dotted with n minus 1. You define this auxiliary function which is a function of lambda and n. Okay. Now, what you want to do to maximize a function, you have to differentiate a function with respect to n, right. So, you want to differentiate L with respect to n, then set it to 0, this equation would be, I am not going to go into deriving this equation, but I am going to give the final result. This will be sigma n minus lambda n equal to 0 and dou L by dou lambda equal to 0 would imply that n dot with n must be equal to 1. Okay. Look at this equation. Further, you have sigma n minus lambda n equal to 0. This I can rewrite it as sigma minus lambda times identity times n is equal to 0, right. Okay. Now, what happens? This is a matrix, this is something like A times n is equal to 0 vector. So, if I were to be able to invert A, what will happen? I will get n as A inverse of 0 matrix 0 vector, which will be 0 vector for n, but I have a constraint that n has to be a unit vector. Okay. So, this is not what I am looking for. So, this matrix should not be invertible, this should not be invertible. What does that mean? That means determinant of sigma minus lambda times identity must be equal to 0. Okay. That matrix has to be, determinant of that matrix has to be 0. Okay. So, now what is this? Determinant of this is, it will be determinant of the matrix sigma xx minus lambda, sigma xy, sigma xz, sigma xy, sigma yy minus lambda, sigma yz, sigma xz, sigma yz, sigma zz minus lambda. I am substituting what is identity matrix, I am expanding this, this has to be equal to 0. Now, it is clear from this equation that when you find the determinant, it will be a cubic polynomial of lambda. So, that cubic polynomial can be written as lambda cube minus k1 lambda square plus k2 lambda minus k3 is equal to 0. This is where the invariance of the stress tensor arises, the principal invariance of the stress tensor arises, where k1, k2, k3 are the principal invariance of the stress tensor, okay, where k1, k2, k3 are the principal invariance of the stress tensor. Okay. So, the solution to this cubic polynomial, you will get 3 real roots, because sigma is a symmetric tensor. Since sigma is a symmetric tensor, you will get 3 real roots for this characteristic equation. This equation, by the way, is called as the characteristic equation. Is called as the characteristic equation, and you will have 3 roots for this, okay, 3 real roots for this equation, which will be the maximum, minimum and middle principal values of the middle value, normal stress values. Okay. We will get 3 roots of this equation, which will be the maximum, minimum and the middle normal stresses that are possible for the given state of stress. Okay. Okay. So, now what happens? You have found 3 roots of lambda, let us say let lambda 1, lambda 2, lambda 3 be the 3 roots of star. Okay. Now, how do I find n? That is the question. How do I find the plane on which this extremum normal stresses occur? Okay. When I substitute sigma minus lambda 1 identity times n equal to 0 vector and the condition that n dot with n must be equal to 1, what I get is a system of 3 equations which I have to solve to get the plane on which this extremum normal stress lambda 1 occurred. Okay. So, basically now what will happen is I can write this matrix sigma xx minus lambda 1 sigma xy sigma xz sigma xy sigma yy minus lambda 1 sigma yz sigma xz sigma yz sigma zz minus lambda 1 into nx1 into ny1 nz1 equal to 0 0 0 and the condition that nx1 squared plus ny1 squared plus nz1 squared must be equal to 1. Okay. nz1 squared must be equal to 1. So, since this determinant was 0, I can't invert this matrix to find that nx1 ny1 nz1 is 0. There will be only 2 equations which are independent. The third equation will be can be derived from the other 2 equations. Okay. Since determinant of sigma minus lambda 1 identity is equal to 0, only 2 of the above 3 equations are independent. Okay. So, what will happen is I will use these 2 independent equations to find nx1 as a function of nz1 and n and ny1 as some other function of nz1. Okay. Okay. Then you substitute for nx1 ny1 these functions in this quadratic equation, then use f of nz1 squared plus g of nz1 squared plus nz1 squared is equal to 1 to find nz1. Okay. So, that way you will find all the 3 components of the normal. So, this in brief is called as the eigenvalue problem. Eigenvalue problem. Okay. You can look up, there are web resources which explain this eigenvalue problem in more detail, which you can look up to gain better understanding of how to find the principal values, which is lambda 1, lambda 2, lambda 3. How do you find the principal direction, which is this nx1, ny1, nz1, nx2, ny2, nz2, nx3, ny3 and nz3. Okay. So, in short what I am getting at is, we saw what a characteristic equation is for a 3-dimensional state of stress. Okay. You will get 3 roots from this characteristic equation, which will be your lambda 1, lambda 2, lambda 3, which in a case of plane stress what will happen is K3 is 0. So, you will get sigma max, sigma min and 0 as the 3 roots for this characteristic equation for plane stress. Okay, where sigma max and sigma min from the Mohr circle equation will be the radius of the Mohr circle plus the center point of the Mohr circle. Okay. So, you know how to find sigma max and sigma min, okay, and the third root would be 0, because k 3 is 0, you can see that lambda equal to 0 is the root of the characteristic equation. Okay. Then the theta that you determine will be the theta that you determine will determine what the normal is. For the principal stress, you found that tan of 2 theta p was 2 times sigma xy by sigma xx minus sigma yy, right. Okay. Now, the normal that will correspond to this is cos of theta p Ex plus sin of theta p Ey. Okay. Okay. So, this normal is the nx1, this will be n1 normal. In other words, this will be n1x Ex plus n1y Ey. If you substitute for lambda 1 equal to sigma max. Okay. Similarly, if I substitute lambda 2 to be sigma min, what I will get is I will get the n2 vector, which will be minus sin theta p Ex plus cos theta p Ey. If I substitute lambda 3 equal to 0 and solve the thing, I will get n3 as Ez vector. Okay. So, these are the principal directions for the plane state of stress. Okay. For the 3 dimensional state of stress, you have to go back to this equation and solve this equation by the method that was outlined here. Okay, by the method that was outlined here. For 3 dimensional state of stress, you have to go back to the stress, this matrix, invert this matrix and use this equation to find nx1, ny1 and g1, whereas for the plane stress, this will be n1, this will be n2 and this will be n3. Okay. So, what you have seen is, you have seen how to find the extremum normal stresses. In the next class, you will see how to find the extremum shear stresses, and then how do you find the shear and normal stresses on a plane called as the octahedral plane. Okay. And that will complete the stress analysis. Thank you.